Hello everybody, welcome to the other star cluster lecture. Let me share my screen. Yeah. We have different designation of star clusters. For example, for cluster of Pleiades, we can call it in different names. For example, in IAU, for example, in galactic coordinates, we can call some clusters like in galactic coordinates or catalogs, different catalogs like ICM or Messier, NGC, and OCL. And also discover, for example, someone who discovers some clusters, they want to name that cluster with their name. For example, Bochum, Basel, Linga, Melot, Stark, and the others. For example, for Pleiades, we have three different names. As you see, M45, Melot 22, and C0344 plus 239. And we have different classification of open clusters that Trumpler built this in three criteria. For example, degree of concentration, range of brightness, number of stars in the cluster, and James and Adler defined the richness class. Open classes can also be classified on the basis of color magnitude diagrams. Trumpler classification. It is in four concentration. The first one is detached clusters with a strong central concentration. The second is detached cluster with little central concentration. The third one is detached cluster with no noticeable concentration. And the fourth one is clusters not well detached, but has a strong field concentration. And in three range of brightness, as you see, the first one is most of the cluster stars are nearly the same apparent brightness. The second is a medium range of brightness between the stars in the cluster. And the third one is cluster is composed of bright and faint stars. And we have different classification for number of stars in the cluster. P shows the poor clusters with less than 50 stars. M defines the medium rich cluster with 50 to 100 stars. R defines the rich clusters with over 100 stars. Open clusters with any type of nebulosity are denoted with an N at the end of the classification. You see here different types of classification. Classic 1, 2, 3, 4. As you see, the concentration is very clear, and they reduce in different ones. For example, in here, you cannot define the central concentration, or here. And also, these are rich in number of stars, or defines the rich. And these are medium, and these are poor in number of stars. Here are the other examples. M46, for example, it is in class 2, and it is rich. M11 is in class 1, 2, and it is also rich. But NGC 6664 is in class 3, and it is not rich, it is in medium. And the last one is NGC 6568. It is in class 4. It is in medium. And this is the planetary nebula in M46. And about the richness class, we have 5 different of richness in class. The first one is less than 25 stars, second between 25 and 50 stars, third one between 50 and 100 stars, fourth between 100 and 250 stars, and fifth is more than 250 stars. As I told you, M11, for example, it is in class 1, 2R, as it is class 2 between 250 stars. It is rich, and the others. And diameters of open clusters, how could we determine the diameter of a star cluster? First, you should find the center of the cluster. For example, here, you should find the center of the cluster. Where is the center? And then from the center, you can count the stars by symmetric. And if it is not symmetric, or if you cannot count it well, correctly, you should shift a bit and then find the center of the cluster, and then again count the number of stars between the center and the far away in a symmetric way. Here you see the 2 clusters, Hafner 10 and Jernik 29. And here, for example, is the center of the cluster, and you can count the stars and go to galactic field that the stars are in the homogeneous with the galactic field. Also in Jernik 29 is the same. And here are 2 other clusters. It is NGC 5999 that discovered many years ago. It is UFMG1 that discovered newly. You see that the center and homogeneous of these clusters are different, and in NGC it is better. Here we can define the diameters of open clusters. As you see, most of the clusters are in less than 10 parsec in diameter, but in different range of the age. Look at T defines the age. It is in million years. And these are globular clusters, but in open clusters, most of the clusters are in diameter less than 10 parsec. As you see here, and just a few open clusters are above the 10 parsec. And this is the other things. It is in pre-Gaia, it is before Gaia, and it is after Gaia. Gaia data release 2 shows the prove the pre-Gaia that most of the clusters are in less than 10 parsec. It is in radius. You can cross it too and have the diameter. It is for most of the clusters. As you see, it proves that yes, most of the clusters are in diameter less than 10 parsec. And maybe you ask that maybe there is a relation between age and diameter. And here someone tested and see that no, there is no correlation between the age and diameter of the clusters in galactic. Also, in galactic center, it is the same as you see in radius or diameter by times 2. Then it is in linear diameter. We see that if we go, it is the same for young and old other clusters, that we see that most of the clusters are in diameter less than 10 parsec. It is not related to the age. Here it is the galactic disk. It is in galactic coordinates, and it is galactic disk, and this is galactic North Pole, and this is galactic South Pole. But you see two, for example, clusters here. Maybe you ask that why they are here in the galactic North Pole and galactic South Pole. We can answer that these are not far away from us, and these are in vicinity of us, but because of the projection effect, as you see, we see them in the poles, north and south poles, but they are not. They are also in the galactic disk. And here you see the motion of the star clusters. Most of the globular clusters are in the galactic center. It is galactic center, and these are globular clusters. And the globular clusters, as you know, they move in different way and go to galactic disk and then go away, follow their way. And these are open clusters. And here is our sun, which move around the galactic center. And this is the spiral arms of the Milky Way. You see, these are spiral arms. And these are open clusters, young clusters, and these are old clusters. In the Gaia data release 1 has not changed our picture of Milky Way, as you see. Most of the open clusters are in the spiral arms. We can see that the material of star clusters are in spiral arms of the galaxy. The star clusters have different direction, as you see here. And these are the spiral arms of the Milky Way, as you see in these pictures. For example, the first one in A, it is the database data set in the galactic disk. The position of the sun is shown by the white cross here. And the galaxy is rotating clockwise. And the second one in B, you see that it is the same as the first one, but showing the measured over density based on a local density scale length 0.3 kiloparsec. And the third one in C, it shows as the same as the before pictures, but showing the wavelength transformation at the scale 3. A different version of panel B and C using a larger scale length can be found in figure B2. Here is a model of our spiral arms of the Milky Way. It is somehow the old model, but you see the spiral arms, and the open classes are in the spiral arms. And this is a new model of spiral arms of our galaxy. You see that somehow they have some overlap interaction to each other with the old and new spiral arms. In here we compare them, the spiral arms of the Milky Way, old model and new model. You see in here it seems that we have more spiral arms and some of them overlap to each other. Here is the spiral arms, but it is not for open classes. These are for Cepheid samples. Here we see the proper motion of the stars for 4,555 groups of the galaxy. Here is the more near or close up to the picture, and you see in here that this line, the difference between lines show the velocity. The length of the line gives the velocity. For example, this one, maybe it is 4 times faster in the velocity than this one. You see that, for example, in this direction, most of them are in the same way, or some of them are in the same way, but in here, no, we have more random or chaotic proper motion. Here we can say that the difference between binary system and two components of moving groups are is that in binary systems they are orbiting to each other with the one center of the gravitation, but two components of moving group do not orbit to each other. They do not round to each other and have no central gravitation between them. In here, you see the visible for the first one in class 1, 2, and 3. It is visible high stellar density at the core with a halo around decreasing in luminosity as a function of the distance from the core. It is M75 is a globular cluster of class 1 in Sagittarius. And this is M62 in a globular cluster of class 4. The core stellar density is still visible, but is more spread out and not as dense. And in here you see that M22 is a globular cluster of class 7 in Sagittarius. The cluster stellar density is more homogeneous and less contrasted. And the last one is M55, is a globular cluster of X1 of class X1 in Sagittarius, and the cluster surface luminosity is completely homogeneous with no increase in stellar density visible at the core. And the smaller the number of stars, the higher the core's stellar density. Here you see the definition ready. It is just related to globular clusters, mostly. And in here, we can say for core radius, distance at which the apparent surface luminosity has dropped by half. And for the second one, half-light radius, distance from the core within which half the total luminosity from the cluster is received. And the third one, half-mass radius, the radius from the core that contains half the total mass. And the most important is tidal radius. The tidal radius, we can measure if the gravitation of the central globular cluster is the same of the gravitation of the outside of the globular cluster. And tidal radius is when the globular cluster is near the galaxy center. It is smaller than the globular cluster, which is far from the galaxy center because of gravitation of pulling of the galactic center. And we can measure the gravitational galactic center and galactic mass from tidal radius. Here is the important observables. For example, single stars, or we can think of star clusters. For example, we can see them by Hertzsprung-Russell diagram, kinematic data, integrated spectra, integrated colors, and polarimetric measurements. And from integrated spectra, we can measure reddening, age, and metallicity. And from polarimetric measurements, we can see how much material is in the star cluster. And for the last one, it is the Hertzsprung-Russell diagram, and it is for open clusters. Here we see the temperature, and here is the absolute visual magnitude. And you see here NGC 2362 is the youngest cluster with the age of around 2 million years. And here you see M67, which is the oldest one with the age around 1.9 × 10⁻⁹ years. And here it is our sun and the other clusters in the Hertzsprung-Russell diagram. Thank you for your attention, and I hope it was useful for you. See you next time. Bye.